Hi, my name is Erika Judith Rivera. I'm from the class of Advanced Reinforced Concrete Design from Florida International University, and today I will be presenting the use of FRPs, fiber reinforced polymers, for retrofitting of short columns. During this presentation, we're going to have a small introduction. Why should we retrofit short columns? The use of FRPs for retrofitting methods and seismic failure modes, different short columns shapes and studies that were performed, a small example, and a conclusion and the reference that I used for this briefing. On January 7, 2020, an earthquake of 6.4 magnitude of Richter scale affected Guanica, Puerto Rico. The earthquake damaged 800 residents and 2,500 residents were declared inhabitable. Most of the construction on the island is typical concrete application and was constructed in between 1970 and 1990 before the recent provisions were incorporated into the designing codes. And as you can see, there's an example of one of the columns, short column damaged in one of residence. Upgrading to the design codes and shear provision have led to a situation in which many old structures are now considered structurally deficient and need rehabilitation or retrofitting. During earthquakes, short columns undergo shear stress due to the low resistance to high imposed horizontal displacement. A practical method to upgrading these shear critical components is by applying external bonding fiber reinforcement polymers, FRPs from this point on, which have been shown to enhance the shear strength significantly. I will be presenting additional research of this topic and different types of retrofitting. And the information in this report was provided by various studies, and the example was completed using the ACI 440.2R/2008 code. So why should we retrofit short columns? Earthquakes are part of the natural hazards that represent a big challenge for engineers, not only in the design phase, but maintenance and serviceability of the structure. Retrofitting will reduce the vulnerability to damage of the existing structure doing seismic activities in the future. Deficiencies to the structure can be due to design error, poor workmanship, degradation of material, corrosion, and past design codes that did not incorporate the provisions of the seismic conditions. In the case of seismic reinforcement, the usual techniques in this category, additional materials, are reinforced concrete jackets, steel plate bonding, FRP jackets and FRP wrapping, and or a combination of the several of the techniques mentioned above. There are other techniques of retrofitting, but in this technical briefing, we will only be discussing the additional materials and only discussing the FRP applications. Existing reinforced concrete structures are inadequately designed for shear. This presents a high risk of catastrophic brittle failure in a seismic event. Short columns attract larger forces due to their high level of stiffness compared to taller ones. The construction of buildings in sloped ground, buildings having mezzanine floors, or non-structural walls and elements are some of the possible situations in which the short column effect could occur. The common damage scale in a short column is in the form of an X-shaped crack due to the shear failure. If the columns are not designed correctly, they could experience a brittle failure with a low energy absorption before forming a practice hinge in the beam. Consequently, short columns in buildings designed with old codes need to be retrofitted. As you can see in this picture taken on January 7 of Guanica, Puerto Rico, this window opening and this non-structural masonry work generated a short column effect on this column, and due to the seismic activity, the column suffered catastrophic damage, compromising the structure. The use of FRPs for retrofitting can be the best option due to the advantage properties: high ratios of resistance to weight, easy to install, and high level of durability, rather than the steel and concrete jackets. According to the above-mentioned advantages, FRP systems have been widely used to strengthen structures elements during previous decades. Reinforced polymers (FRPs) materials are composed of material that typically consists of strong fibers embedded in a resin matrix. The fiber provides a strength and stiffness to the composition and generally carries most of the applied loads. Common use of materials used for fibers are glass, carbon, and synthetic fibers. And FRP components are very high strength characteristics and non-conductive, non-corrosive, and lightweight. Compared to the concrete and steel jackets, composite jackets have the advantage in speed and easy installation, reduces maintenance, high strength, and better fatigue performance, and as well as lightweight and superior durability. Here is an example of a round column wrapped around with FRPs, and you see the strength applied to the confinement area and the load applied. So the FRP will work with the confinement of the column. And below is an example of what a FRP wrap or fiber would look like. There are different retrofitting methods and seismic failures. Of the retrofitting methods that are available for FRPs are composite jackets, partial interactions, and circle oval shaped steel hybrid jacket for square or rectangular sections, which is a combination in between steel plates and FRPs. This is an area of investigation that different techniques continue to evolve. Potential seismic failure modes that we should evaluate different structures to see if retrofitting is required are shear failure, flexural plastic hinge failure due to the large displacement where flexural cracking covers the concrete spoiling, buckling of the longitudinal reinforcement, and cracking of the core concrete cause significant deterioration of the plastic hinge, and existing columns that have the lap splice of the longitudinal reinforcement at the bottom where the maximum flexural moment and here's a potential plastic hinge occurs. These are the majority of the structures built before 1971 that had this condition. So those are things that we have to evaluate, that these structures can have potential failure and they shall be retrofitted. The geometric shape of the column has a significant role on the column's failure mode and influence in the effectiveness of the FRP on the confinement. In the circular short column, when a circular jacket is applied to a column, this results in an increase in the strength and the deformation capacity. The passive confinement generated by the FRP jacket will prevent the increase in the perimeter length and contain the concrete expansion. The circle shape is the most effective in providing confinement, and as a result, increases the strength and the ductility of the column. For a rectangular short column, the effective of the FRP jacket strategy in the rectangular column is less than the square and the circular section, and is less in the weak axle than in the strong axle. The rectilinear short column, the behavior of the completely wrapped column changed from brittle failure to a ductile bending failure. And the challenge of the rectangular and the rectilinear short column is that the corners does not permit the wrap or the jacket to fasten completely, which provides a weak spot from the confinement. In this table, we have the representation of the rectilinear short column studied, which indicated 8 columns with the same dimension and same material. SC1 was the control column, and compared to the control column, all the other columns that had FRPs had an increase in ultimate load and ultimate displacement compared to the control column, and also had a change in the failure mode, as you could see in the table. For the example, we're going to draw the interaction diagram for AC 440.2R-08. We're going to be working on a fully wrapped with FRP column 12 by 12 inches FC of 6.19 KSI and the additional data or properties provided. The effective confining pressure, FL, equals 2 times the 4 sides times the thickness of the FRP times the mold elasticity of the FRP times KE, which is a reduction factor, times the strain of the FRP divided by D, which is the base squared plus the height squared. That's all equal to 0.902 KSI. The minimum confinement ratio is FL over FC, which is equal to 0.14572, which is bigger than 0.08, which means that the stress strain curve is ascending. To create the moment axial force interaction diagram, we have to start calculating the different points. So for point A, the longitudinal steel reinforcement ratio, which has been calculated in different exercises during the course, we calculate the effective area to concrete area ratio, which takes in consideration the radius of the corners of the column, which is important for the FRP, the strength and strain effective factor, Ka and Kb, the confined actual compressive strength, which is FCC, which takes a reduction factor of 0.95 for the FRP, and the maximum actual compression strain. Then you calculate the actual load without the factored, which gave 1,142.28 kips. Then you incorporate, in accordance to the AC 440.2R-08, two factors of 0.6 and 0.8, which gives you 593.98 kips. I repeated this procedure to the other points, and I did the adjustments corresponding to the different procedures established in the code. And I also decided to evaluate the column like if it was in slenderness and as a short column. So using previous procedures to determine the moment actual force interaction diagram for short columns and slender columns, I used the same dimensions and properties of the column of the FRPs without the FRP influence, and incorporated it in the diagram with the FRP information. As you can see, we have the interaction diagram with the slenderness being in orange, the short column being blue, and the green being with the FRP influence. We could see that the moment capacity of the FRP is greater than the one without the FRP. To conclude this presentation, the FRPs are utilized because of the fast and easy installation, low maintenance, durability, and the enhancement in strength, ductility, energy dissipation, and FACT performance makes it a viable option of retrofitting economically challenged community to provide resilience in a sustainable way. Studies: Colomb 2007, Hamid 2020, and AHA 2019 demonstrated that the influence of FRPs to the column strength, energy dissipation, and ductility increased compared to the control columns. These are the references that I used to put together this technical briefing. Thank you.